Okay, so let's continue from last time. So we're still in introduction. I'm basically walking through the parts I want to cover in this course. So last time we said that at the beginning we had using various different methods. Then we proceed to causal relations, and the difference is for statistical relation, our target function, right? So remember target function. So our target function is oftentimes EY given X. That's our target function because we want to use X to predict Y. Okay, so statistically that's what we want to do. Now for causal inference or causal effects, our target function oftentimes is EY given do X. Okay, given do X, meaning that if we are actually going to set the value of X, manipulate it, and we want to see what the Y value is. Okay, so that's the causal. That's a causal. That's non-causal, right? So that's oftentimes our different target function. So how do we learn? How do we learn this, right? How do we learn this target function? So we said the simplest way to do is to basically just do it. Okay, just do it. Just set X equal to a certain value, like Y, like 1, and see what the Y value is, and average them, and you get this EY given do X. Okay, so the simplest way, just do it. Okay, and empirically that means, in practice that means if you simply want to do it, you just do experiments, right? Experiments is basically you put all these different people, you pick them apart. So you let these people, you set these people X equal to 0, and you set X equal to 1 here, and you see what's the Y value, and that give you an estimate. Right? So this is the simplest way to do it. But oftentimes we cannot do experiments. The reason why we cannot do experiments in economics is because, for example, many macro policies like monetary policy, you just cannot force countries to do experiments with you, right? You cannot force a country to do a certain monetary experiment and see how it goes. And also there's another reason, which is oftentimes, yes, we could do experiments, okay? It's possible to do experiments. But the results from experiments are not particularly trustworthy. So we cannot trust the results very much. Why? Because economics, we study human beings. And human beings are not like atoms and molecules. Human beings are much more diverse and complicated. So whatever experiments you do on some individuals, some human beings, you cannot assume that they apply to other human beings. Okay, so in economics, as you all know, we have this discipline called behavioral economics, right? And we also have development economics where people do large field experiments. So I'm getting good at it. So these things, if you do let's say, behavioral economics, what people typically do is, hey, I want to study how people behave, okay, in a certain situations. So they put some people into a laboratory, right? We have here at this university. You put people into a laboratory lab, you do experiments, and you see how people respond, and you write a paper out of it. The problem is you only get to see the response of these individuals, like these students here, which by no means represent the global population of human beings, right? Because we are so diverse. And this is the key difference between economics and something like physics, where in physics, everywhere you set up a lab, you study some molecules, you study some atoms, they are going to be everywhere the same, right? So your result is more, generalizable. And in economics, our results from labs are not very generalizable. So oftentimes we cannot use experiments, okay, to rely on experiments to derive our lessons. So what can we do? Well, oftentimes in economics, we have to rely on our observed data. Not experiments, but observed data. But getting causal relation out of observed data becomes much harder. Okay, becomes much harder. And one of the reasons is in experiments you can just do it. Okay, you just can let person do this and do that. Okay, and take this drug and do not take this drug and then see the result. In observational data, the data come from our observation, meaning you cannot force people to do something. So in observations, when you see people actually do something, right? When you see people have X equal to 1 or X equal to 0, meaning in observations, when you see people take the drug or when you see people do not take the drug, it is because they want to take the drug and they do not want to take the drug. And it means what? It means people are selecting their own x, okay? They're selecting their own x. And which means that people who select x equal to 1 and the people who select x equal to 0, in many cases, are likely to be very different people. Okay? They are likely to be very different people. So in the example I just gave last time, when we talked about hospitals, so there's hospital A, hospital B. You cannot simply compare hospital A's recovery rate with hospital B. Why? Because the people who go to hospital A and the people who go to hospital B could be very different. It could be very different. Now, one simple case is hospital B is actually better. So people who are very sick go to hospital B. But people who are not sick, they go to hospital A, right? So people make this choice themselves. Instead of you let them do, okay, you force them to do. That's in economics is called a self-selection effect or self-selection bias. Okay? So anytime, because in economics, we study behavior, human behavior. And because human behavior are essentially chosen by people themselves. And if you are not careful, you have this self-selection bias, which is the actions chosen by themselves. So when you compare two different actions, you are comparing two different group of people who make different choices. And you simply compare their why, it tells you a bad story, not the correct story, okay, the wrong story. So much of causal inference is, the problem of causal inference is how to overcome this self-selection bias, okay? In our introduction, I just want to walk you through a very basic method of dealing not only with self-selection, but a general method of how to deal with causal inference, how to get causal inference result, okay? So this method is this. It turns out that in order to get causal inference, in order to estimate causal effect, it turns out that we need something more than just data. Okay, we need the data we observe. We also need some theory. We need a theory. The theory is how do variables actually relate to each other in the data, in terms of mechanism. What is the mechanism behind the data? So if we want to know, okay, so if I want to know x, the causal effect of x on y, it turns out that I not only need the data on x and data on y, I need what? I need an understanding, a theory of how x could affect y. I need the mechanism first before I can go on to estimate the causal effect. All right. So now, if you're not clear what I mean, give me a second. Okay, give me a second. It's actually very simple. All right, so it turns out, okay, so let's suppose there are three variables. Suppose there are actually A, B, C, right? Suppose there are A, B, C, three variables. Now, we could have some theory about the relation between these three variables, like how they affect each other. We have a theory. And, there are some very basic relation between the three. For example, it could be what? It could be A has a direct causal effect on C. Okay, A affects C. I will use this, I will draw this very simple diagram. A affects C, and C affects B. Okay, so this is one relationship, which is very easy. The other relationship is A will cause C, and B will cause C. Okay, B will cause C. So this is another kind of relationship between the three. Well, it could be that C cause A, and C cause B. So these are three very simple relationships. Of course, you can add more, right? You can make it more complicated, but we stop here, right? So this is called what? This is called C is a common effect of A and B. This is called C is common cause of A and B. This is here C is in the middle, so it's called a mediator. Okay, so it's somewhere in the middle of A and B. So once we have three variables, if we only have three variables, we can already write down different ways that these three variables could affect each other. And this is called, each way is called a mechanism. Okay? Each way is basically a mechanism in which things basically are created in this world, okay? How the data is created. We need this mechanism first before we can go on to estimate causal effects. So causal effects no longer depend only on the data, but on our assumption about what could be going on between these variables. Okay, so we will see more examples. But let's consider some basic examples of what these different relationships means. Okay. So let me ask you. Now we instead of using ABC, I'm going to use LAY. Okay. Just a different. So suppose I have three variables called L, A, and Y, and L actually cause A. Okay, I assume. So I think L causes Y, and I think L causes A, and I think L causes Y. Okay. All right. Suppose. Okay. Suppose A and Y has no relation. A does not cause Y. Y does not cause A. There is no causal effect. Okay. A does not have causal effect on Y. Y doesn't have causal effect on A. Then I ask you with this question: is A and Y independent or correlated? Are the two correlated or are they independent? So by the way, independence, I use this notation, okay, independent. So if they're independent, right, if they're not independent, they're not independent, they're correlated. So is A and Y correlated or are they independent? What do you think? Okay, why? Because they are, okay? They are correlated. Now, give you an example, okay, very simple example. Suppose A is whether you carry a lighter, okay? People know what lighter is, right? Okay, 打火机, okay? So suppose whether you carry a lighter, so A is 0, 1, okay? 0 you do not carry, 1 you carry. Y, L is smoking, okay? Whether you smoke, 0 do not smoke, 1 smoke. Y is very unfortunate, Y is lung cancer, okay? So we are a little bit extreme here. But look, smoke can lead to lung cancer. And smoking can cause you to always carry a lighter with you, right? Okay? So there are direct causal effect. But carrying a lighter, does it have a causal effect on lung cancer? No, right? Obviously not. Okay? But are they correlated? So if you see a person always carrying a lighter with him, you know what? You know this person likely smokes and likely has a higher probability of having a lung cancer, right? Okay? So if you so there are two people, one person, you have no other data, but you see two people, one person always carry a lighter. You do not see him smoke, but you see him always carry a lighter. You know he always carry a lighter. The other person does not carry a lighter at all. Then you could predict the first person to have a higher probability of getting lung cancer. All right? Because why? Because they are correlated. A and Y are correlated. And the reason why they are correlated is because there is a single factor, like smoking, causing both of them. Okay, causing them. Okay, so this is just one example, right? Now, in other words, A and Y is not independent when there's something called L, when there's something that causes both of them. If they have a common cause, then they are no longer independent. They are correlated. Okay, now think about what we are trying to do. We are trying to estimate this, okay? We're trying to estimate EY given to A, okay? Suppose, right? We're trying to estimate EY given to A. I want to know the causal effect of A on Y. What I could do, okay? What I can see from the data is EY given A, right? So this is what I see from the data, which is this part is the correlation. This is the causation. So let me ask you, in this case, is correlation equal to causation or not? Equal to causation or not? They are not. Okay. Now, actually, let me rephrase my question. Now, suppose my model is this. Okay. Suppose my model or my theory is L causes A and L causes Y, and I know that A could, but I do not know. Okay. I think A may have causal effect on Y, but I'm not sure. So I want to basically estimate this causal effect. Is it 0 or is it not 0? Now what I can do is I can go to data, I can look at the correlation between A and Y. But the question is, does the correlation tell me the causation? No. The answer is no. Why? Because if there's no causation, they are still correlated. Okay, the reason is, even without causation, they are correlated. So if I see correlation, that doesn't tell me causation. Okay? So because without causation, they are still what? Correlated. Okay, they are still correlated. So I cannot do that. So this is a one major case in which correlation is not equal to causation. Right? Okay? All right. Now, okay. We also can have another example here, right? Also have another example here. So suppose L is what? Suppose L is how sick you are. Okay, sickness. So this using our hospital example. L is how sickness you are. Now, how sick you are will influence, will basically cause you to pick your hospital. Okay, so it will be a hospital. So if you're sick, you go to a major hospital. If you're not that sick, you go to a local small hospital, right? So your sickness affects your hospital choice. Now, your sickness obviously affects whether you recover, right? Whether you recover from Y. And the quality of your hospital, of course, also affects Y. Okay? So we already learned from our example before, when we talk about hospital, we know that you cannot simply compare recovery rate of two different hospitals because people can choose to go to different hospitals. And we can use this, right? This is called a causal diagram. So we can use this simple causal diagram to represent what we were really saying about that example, right? Remember? Okay? Remember we have example where we have A and B, two hospitals. We say, this hospital people recover lower rate, this higher rate, but you cannot compare them to say this hospital is the higher quality because it could be that this hospital is actually better. And so sicker people go to this hospital. That's what we're saying about that story. We say, okay, from that story, we learn that you cannot trust correlation. But what exactly are we saying there is actually this story, okay? So this is our underlying model about that story. Basically, we say people's sickness determine which hospital they go to, and the sickness determining how quick they recover. And the hospital may also affect how quick they recover. If this is the story, then we know that we cannot trust correlation. Okay? Why we cannot trust correlation? Because even without causation, these two will become correlated simply because of the common cause. Okay, common cause. That's what this model tells us. Okay, that's what this model tells us. All right. How about this case? Okay, how about this case? How about when I have this relationship where it's really A and a Y, and they have no causal effect on each other, but A causes L and a Y causes L. So L is their common effect. Okay, the L is a common effect. If this is the case, is A and a Y independent, or are they correlated? Depends on what? Independent or dependent? In this case, they're independent. Okay, there will not be any correlation. Okay, if they simply cause the same thing, it's okay. They don't have any correlation. The example would be A will be family heart history, heart disease history. Okay, family history. Okay, whether people have heart disease in this family. Now, this family history will affect whether you have heart disease. Okay, whether you have heart attack or heart attack. Now, why could it again be smoking? Okay, why could it again be smoking? So obviously, if you smoke, you actually increase your heart attack rate. If you have family history, it also affects your heart attack rate. But whether you smoke and your family history of heart attack has nothing to do with each other. So they're completely independent. Okay, they're completely independent. Okay, so in this case, suppose my theory or my model is my theory is A causes L, Y causes L, but suppose I think A can also cause L, but I'm not sure. So this is what I want to know, okay? This is what I want to know. What is the causal effect of A on Y? That's what I want to know. If that's the case, can I just get this effect from EY given A? In this case, is EY given A equal to EY given do A? That's the question. Are they equal? Is correlation equal to causation here? And the question is, and the answer is yes. In this case, correlation equals causation. Why? Why does correlation tell us causation here? Because they're independent. Yeah. Because without this causation, suppose there's no causation. Okay. Suppose there's no causation, there will be no correlation. So if you see any correlation, that correlation has to be because of the causation. Okay, it has to be because of it. So if the relationship between A, Y, and L is this kind of relationship, then correlation tells you causation. You can immediately get it from the data. Okay, from the data. All right, so you can see that our effort here is really to determine in what circumstance correlation equals causation, and in what circumstance correlation does not equal to causation. So in this case, correlation equals causation. Okay, between A and Y, All right, because once you delete the causation, you get no correlation. We know that because that's our theory. Okay, that's how we understand the relation between these variables. Okay, all right. Now let's come back to our early example. Come back to our early example. We still have L, and this L will actually cause you to do. So this L will give you A, and this L will cause Y. Okay, and A may cause Y. We do not know. We want to find this out. Okay, so we said in this example, correlation does not equal causation, because once you get rid of causation, you still have correlation. So when you see correlation, it may not be causation. It could be just be this. Okay, so how do we deal with this problem? Well, one thing we can do is we can condition on L. Okay, we can condition on L. So what does condition mean? Now, if you think about what does condition mean, right? So you have studied conditional probability, but what exactly does condition mean intuitively? Well, intuitively, conditional on something means you fix this thing. You do not want it to change. Okay. So for example, suppose so again, this is smoking, right? So this is smoke, and this is lighter, and this is cancer, right? This is cancer. Now, if I look at people who, if I look at the conditional so if we look at, let's say, probability, okay? So if we look at conditional probability y conditional A, so that's the correlation. But now I'm going to look at not only y conditional A, but I'm also conditional on L, okay? I'm also going to conditional. Well, actually, I'm sorry. Let me do this. I want to say A and Y. Is A and Y independent? No. A and Y is correlated. But what if I condition on L? And for example, suppose I conditional on L equal to 0. Okay, conditional equal to 0. By condition on L equal to 0, it means what? It means we only look at people who do not smoke. Right? So there's a whole population, but we only take the people who do not smoke. We take them out and only look at them. So I fix the population to essentially to a subpopulation where L equal to 0. Now tell me, in this population, in the population where people do not smoke, is carrying a lighter and the probability of lung cancer correlated? No, right? No. Okay? For people who do not smoke, I could carry a lighter too, because I don't know, I want to play with matches and stuff, right? But obviously that has nothing to do with my probability of cancer. So once I condition, then they become independent. Right? They become independent. Okay. So now that I know this, right? How can I get causal effect of A on Y? How do I get it? Well, one way to get it is this, okay? Because of this effect, I know that Y conditional on A is not equal to Y conditional on do A, okay? Do A. They are different. They are not the same. Correlation does not equal to causation in this case. However, if I also condition on L, okay? If I also condition on L, then correlation becomes causation again. Okay? And the reason is, if I condition on L, then A and Y will become independent if there is no causation. They will become independent. So if I condition on L, and I still see some correlation between A and Y, if I still see some correlation, it has to be because there is a causation here. Okay? So once you condition on L, then any correlation between A and Y must be because there is causation. So correlation equal to causation. In this case, basically we have this relation. Okay? So do and not do, they are the same. They are the same thing. And that's how we get causal effect, right? Out of data. All right? Okay. Now, so what we are saying here is this. We're saying here is, look, A and Y are not independent. I can make them independent by condition on L. Okay, by condition L. Now, we can do the reverse. The reverse is this. The reverse is A will cause L, and Y will cause L, right? In this case, I know A and Y is actually independent. They're not correlated. but I can make them correlated by condition on L. I can do that. Okay. Once I condition on L, A and Y will become correlated. It's like flipping a switch. Why is this? Why is this? Well, think about our case. Okay, think about our case. Suppose using our example. Okay, using our previous example. Suppose A is family history. Okay, family history. A is family history. Y is smoking. Okay, and L is heart attack. Okay, heart attack. Now both can cause heart attack. If I conditional on heart attack, suppose I only look at people who actually end up getting heart attack. Suppose I only look at people who get heart attack. Among these people, these two will become correlated and negatively correlated. Why is that the case? Because hey, you can get a heart attack either from your history, either from your parents, okay, family history, or from your smoking. So if I see you get a heart attack, and I know you have family history, then it's less likely you also smoke, right? Okay? Because one of them gets you this, right? One of them gets you this. So if I know that you have this, then it's less likely you get this. If I know that you smoke, then it's more likely because smoke, so you're less likely to have this. Then they become correlated and also negatively correlated. Okay? Negatively correlated. Right? Do people get it? Now, this, using another example, example would be this. Okay, example will be, let's say you are getting into a university, right? You're getting into a very good university. Now, in order to get into this university, so L would be whether you are actually in a university, whether you're actually getting into that very good university. So A will be what? A will be your, I don't know, you'll be literature, right? You have a literature test. And then Y will be you'll have a math test. You have a math test. So if you score very high on literature, even though your math may not be very good, you get in, right? Qian Zhongshu got into Tsinghua with a math of 29, right? That's what the historical data says. Or you can get into a very good university with a very high math, but not so good literature. Of course, if you're high both, then you're getting. Now, I'm going to make an assumption that your literature score and your math score has no relation. Okay, has no relation. They're independent. They do not have causal effect on each other. They're not correlated. Okay, so I'm going to make that assumption. All right, but I know that they both cause you to enter this university. Now, they're independent. Okay, now they're independent. They have no relation. But once I conditional on L equal to 1, meaning I only look at the people in this university. Okay, so I pick a random person in this university. I ask him, what is your literature score? And he says, I basically get everything. Okay, I'm 4 score. Okay, I get the highest score possible in literature. Then you can say it's less likely that this person also has a very high math score, right? Because you get in whether you have high literature or high math. So I already see you have high literature, then it's less likely you have high math. Do people get it? No? Still no? Right? You can get to this result using either one. So once you have one of them, then it's less likely for you to do that. Okay? So in summation, we have this. Suppose we have A, B, C, 3 variables. Or let's just say, okay, suppose I have X and Y, 2 variables. Why is X and Y correlated, right? What are the reasons X could be correlated to Y? Well, there are several reasons. The first reason is X has a direct causal effect on Y, or Y has a direct causal effect on X. This is the first reason that they may be correlated. The second reason they are correlated is there's something else. Okay, there's something else that is causing both of them. Okay, that's causing both of them. That's the second reason. And the third reason is they all lead to something else, and I condition on them, and that also makes them correlated. I will convince you more on this. Okay, but that's true. So that's basically 3 reasons why X and Y may be correlated. So how do we get causal effect? How do we get the causal effect of X and Y? Well, very simple. If this is the case, if something is causing both X and Y, then I need to condition on this. I need to condition. Once I condition, then whatever is left is the causal effect. So if I condition on them, then correlation equal to causation. Now, on the other hand, I have to make sure I do not condition on any common effect. So the very basic strategy of getting causal effect from data, okay, is to condition on any common effect and do not condition on any common cause. That basically give you the if you do that, then correlation will equal causation. So in this case, then you can get everything you want from the data. That is the basic strategy. Okay, that's the basic strategy. So example, right? As an example, this is the education and the earning example we are all familiar with, right? So we know that how many years of education, right? So E is your education level, Y is how much you earn. We know that you cannot simply look at what? You cannot simply look at EY given, well, let me do S, okay? EY given S. S is your schooling, okay? Years of education. We know that you cannot simply look at this because this only tells you correlation, not causation. And the reason why, right? Why we cannot look at this, or why correlation does not equal causation? Because what? Because we say that people who have high ability get more education, and people who have high ability earn more, right? Earn more, okay? So what is the ability here? Right? We know that people with high ability get more education, and people who have higher ability earn more. So if you see people have higher education earn more, it may not be education, it may be ability, right? That's the typical explanation you were given in econometrics. But so what is the ability here? The ability is basically a common cause, okay? A common cause. Ability cause you to have more education. Ability cause you to have more earning, have more income. And because ability is a common cause, we cannot do this. Okay? Because S and Y will be correlated, even if there's no, right? Even if there's no, they will be correlated. But also, of course, we also think there's something here, right? We say there's also something here, and we want to find it out. We want to find out what is the causation of schooling education on Y. That's what we try to find out. And how do we do it? Very simple. We condition on A, right? We condition on A. And by condition on A, I mean we only look at people who have the same ability, okay? We only look at people who have the same ability. And we compare, and then we compare their earning and their schooling and their education level. That should tell us the story of the true causal effect. Because once we're conditioned on it, this, whatever correlation is left becomes the causation. Now, how do I have ability, right? We don't see ability directly. But suppose I have all your test scores, right? Your test scores. And suppose test score is a pretty good measurement of ability. Then I can just use your test scores, okay? So I can basically look at people who have the same test scores, very similar test scores. And we look at their education level and their earnings and see what is the true relationship or the causal relation between education and earnings. Okay? All right. So let's do this. So I want to know. So basically, what I'm saying here is I want to know EY. Okay, EY given do S. This is what I want to know. Okay, causal effect. The causal effect of education on earnings. I can write it. Okay, I can write it this way. I can write it as EY given do S. Okay, do S. And I'm going to what? I'm going to condition on your ability, okay? Also on ability. And here, let the ability be your test score, okay? Suppose I have data on test score. I'm going to condition on test score. And suppose A has 1 to 10 different levels, okay? Well, actually, let's say A has 1 to 4 levels, GPA, right? So this will be, DE, this will be A plus, okay? 1 to 4. Then I can say, okay, suppose this is A1, right? And then I have A equal 2 and equal 3, A equal to 4, right? I can do all this. Then I can add all the A together, right? A equal to 1, 2, 4. I can add all of them together. That should give us this, right? This is just a very basic calculation. Okay? Condition on one more thing and add them together to give you the original thing. Now the trick here is this. The trick is this step, which is I realize what is this thing equal to? What is this thing equal to? Well, this thing is equal to EY given as A. EY given as A. Correlation equal to causation. Right. Do people understand? Because once you condition on A, then whatever correlation between S and Y equal to causation between S and Y. That's essentially what we're saying. Okay? Once I condition on A, then correlation becomes equal to causation. So the trick here is I realize this, so I condition on A, and then whatever is left, okay, the correlation will tell me the causation, and they become essentially equal. So basically, I can write this equal to summation of A, and I missed something else. Okay, I realized I missed something else. It's actually summation of A, but also there's a PA here. Okay, right? Sorry about that. Right? There's a distribution. There's a probability of A here. Okay, so I basically add a probability of A here. Okay, add a probability, and that will give me this causal relation. Okay, so we start from here. Okay, I want to know causal effect. And what I do is I read from my causal graph, okay, from my causal diagram, I realize that I need to condition on A. So condition on A, once I condition on A, this becomes statistical, right? This correlation becomes causation. So I can write it this way. Now, once I can write it this way, then everything here, I can get it directly from data. How do I get this from data? How do I get this from data? How do I get EY given SA from data? Like how do I get this thing? Well, that's just the thing that we have talked about in our lecture 1, which is how do you get. So let me recap, okay? So what we're doing here is this is our original target function. This is our target function originally. We want to learn this, and we basically say, okay, if you want to learn this, I only need to learn this, okay? So this becomes our new target function, which is EY given SA. And how do I learn this new target function? It's easy, okay? It's easy. It's just basically what we talk about. Suppose we have S equal to 1, A equal to 1, and you have many Y data points. Then you want to learn EY given SA, you just average all these Y data points. That's called a non-parametric. And then if you do not have a lot of Y, okay, so you have only one point here, then what you do is you need a model. And so, suppose this is S, these are A, and this is Y, and then you may have these data points. Then you can have a linear model, you can have a polynomial model, you can have whatever model is, then you do your model selection. That is essentially what we're doing, right, in our first, in the first part where we talk about. Okay, so let's go back to our graph. Okay, right. So how do we get EY given SA? Well, we look at the data of SA and Y. And then we say, okay, we can fit a linear model, we can fit more complex, and then we can pick the one that basically give us the best result. Okay, where do I pick? Well, I pick this one, right? I pick this one here. Because that's the one that's the best. Okay, so everything so this is the connection. This is the connection between statistical learning, right? Machine learning, statistical machine learning. This is the connection between statistical machine learning and causal inference. Basically, our goal in causal inference, what we are doing essentially is two-step. The first step is, okay, this is the causal effect we want to know. The first step is ask, how can I turn this causal effect into simple, non-causal statistical correlation? How can I turn this into statistical correlation? Well, here I know that if I condition on A, then I can turn it into statistical correlation. So once I turn it into a statistical correlation problem, then I can use all the tools we have learned you have in machine learning and statistics to model this, okay, to model this relationship, okay, using the best model you have. And that is the connection. Now, in traditional econometrics, the way that you traditionally do in econometrics is that you don't do all this machine learning stuff. You say, okay, how do I get EY given SA? I just assume a linear model. What is a linear model? Y equal to beta 0 plus beta 1 S plus beta 2A, right? Plus beta 2A. This is a linear model. That's what you traditionally do, okay? That's what basically traditionally you say, okay, suppose I see your schooling, your education level, your income. Suppose I have your measurement of your ability, your test score stuff. Then I can just do a simple linear regression. And that should tell me the causal effect. That's what we traditionally do. But there's no reason to use only a linear model. Okay? You can use any model you want to model EY given SA. Any complicated model you want. The best model that fits the relation. The key is realizing that in order to get this, we can transform the problem into this. And that is the key, okay, in causal inference. All right? I hope. If you feel that you do not understand the points, perfectly okay, because this is just introduction. I'm just going over like what I want to go over later in this course. So this is a basic overview, some basic concepts I want you to. In fact, causal inference is much more complicated than this makes causal inference actually look easy, because this is saying, look, if I have, if I just have L equal to L given A, L given Y, if I have just a relationship, let me just condition on this, and I get everything. Okay, I just get my causal effect. This looks simple, but in reality, it's not simple at all. Why? Because oftentimes we do not have this L. We just do not have this L. Okay, so ability, we do not have ability. Now, suppose I also do not have test scores. Or if you think that test score doesn't represent ability at all, what can you do, right? So we will learn, okay? We will learn a series of different techniques that helps us to learn the causal effect if we do not observe this or if we do not observe that. That's essentially everything about causal inference we're going to learn. Okay? On to our next topic, right? Let me just say, by the way, I already said, okay? On to our next topic. Our next topic is called structural estimation. Now, structural estimation is for undergrad students like you, or even for most grad students here, they do not know, okay? They have never touched structural estimation, but this is a very important topic in econometrics. So basic is this. When you study econometrics, it often feels like, I don't know about you, but it may feel like that it has nothing to do with the theory course you have learned. So in economics, you study two kinds of course. In one kind of course, that's econometrics, statistics, and all that stuff. The other kind of course is theory course, right? You see also micro, macro, game theory, right? Financial theory, all this theory. Is there a connection between the two? So when you do econometrics, do you use any theory? I guess that's the question. Or not? Okay? Probably not. Probably not. So think about it. For example, education and wage, right? Education and wage. So this is your education. This is how many education you have. Again, this is how many earnings, right? How many wage you earn. And I want to know the causal effect of education on wage. So I say, okay, that's conditional on your ability, right? That's conditional on ability, and then we're done. But there's no economic theory here. We have a theory, right? This is our theory, okay? This is our model. This is our theory. But what does economics say about how wage actually comes about, right? Like why? What determines wage? So suppose I say, suppose education is 0, 1, okay? Suppose 0 means you do not have college education. 1 means you have college education. W is the wage of college students versus non-college students, okay? Non-college students. What determines that? What determines W? In economic theory, what determines it? Yeah, supply, demand, right? Labor, supply, labor, demand. How many, So we have a supply of college students. The higher the wage, the more people go to college. The more college wage, and there's a demand, right? There's a demand curve, there's a supply curve. This is the wage, right? So this wage is the wage here, right? The wage here. In other words, the wage that you earn as a college student depends not only on whether you go to college, it depends on whether other people go to college and how many people go to college. And it also depends on the demand, right? What kind of economy you have. Okay, what kind of economy you have. All these factors together determine your wage. But unfortunately, when we do our analysis, we do not use this, right? We have no use for this theory. It's like economic theory is just theory. And then we have our econometrics. It seems that they're completely, disconnected, which is unfortunate, right? Which is not the way it should be. So here's the difference. Here's the thing. In econometrics, econometric analysis, there are actually two schools, different schools. One school is called reduced form, okay? So one school is called reduced form. So what is reduced form? Reduced form is basically like this, okay? So I'm going to assume some relationship, underlying model, and I'm just going to, okay, so EY given W and conditional A. I just want to find this out. That's reduced form. We're not using any, we're not really estimating an economic model that much, okay? So that's reduced form. There's another approach. There's another approach which is called structural. Okay, structural. Okay. Structural model or structural estimation. Structural. So with structural estimation, these are actually two different schools. Okay, they reduced form people sometimes structural people have been fighting with each other for a long time. Econometrics, and I will tell you not today. Okay, maybe not this time, but I will tell you later how you can unite them. Okay, what's the coherent framework for understanding them? But what structural people try to do is instead of doing this, okay, we structural people try to what? Try to estimate an actual economic model, a theory. Okay, for example, like a supply and demand. Okay, I'm going to say, okay, the wage is determined by supply and demand. So I'm going to estimate the supply curve, and I'm going to estimate the demand curve of the economy, so that I can really figure out the relationship between wage and education, rather than doing this. Okay, so that's basically structural. Structural is basically estimating economic theory. You can think about it in that case. All right, and I'll tell you what their connection is. But let's take a look at an example. Okay, so I'm going to show you two examples of structural estimation, and show you how structural estimation can be actually pretty powerful. It can be pretty powerful. In some cases, it could be much more powerful than reduced form approach of causal inference. All right. So the first example is auction. Now, how many of you have studied the game theory? All of you? Okay. Well, some of you have studied game theory. Some of you have not. If you have not, don't worry. You just trust me. All right. I'm just going to trust you. Okay. So, one of the simplest model in game theory is an auction model. So what is auction? Auction is a bunch of, you know what auction is. A bunch of people participate and bid for the thing. And in one of the simplest auction format, it's called a first price seal bid auction, which means everybody just, you just write your price in an envelope, you seal it, you give it to the auctioneer. Auctioneer opens all the envelopes, and whoever has the highest bid wins this item. Okay, wins the item. All right. Now, suppose I have a bunch of the same paintings. Suppose a painter paints 20 paintings, all the same paintings. Just paints 20 of them. There are 20 copies. Well, actually, there are more than 20 copies. I'm sorry, but these are all the same paintings. And I'm going to run this auction many different times. And every time, the x variable is the number of bidders. How many people take part in the auction? Y is the winning bid. So we can see that there's actually some positive correlation between the two. The more people participate in auction, the higher the winning bid. Now you can think about why, okay? But that's the case, okay? That's what the data tells. Now, suppose what I want to do is this. I'm an auctioneer. I'm going to organize a new auction. I'm going to do a new auction of the same thing, but this time I'm going to have many more bidders. I'm going to include 50 bidders, okay? 50 bidders. I want to estimate, or I want to predict what is going to be my income. Okay, what is going to be my winning bid? How much money can I take in if I allow 50 people to participate? Okay, so how do you do it? Well, it's very simple. What you can do is so you want to predict what happens when x equals to 50. Then I can just simply draw a line, right? Yeah. I can do a linear regression. No? Why? Why not? Why not?
Because the 50 is very far away from the sample.
So then why? Then what does it mean?
There's no internal validity.
Okay, you're jumping ahead, right? You're jumping ahead. So actually not internal, it should be external, but anyway, so we can talk about it later. So one of the ways we can do it is to simply fit a statistical model onto the data. So I can fit a linear line. I can also, but does the linear line look good? Probably not, right? I can also fit a polynomial, right? I can also fit something like this. And then I can tell you what goes on if x equal to 50. I can do that. Okay? There's another approach. There's another way to do it. Sorry, you have?
Oh, no, I just want to look on why
Y is nonlinear, right? Yeah, so I can do a polynomial, can I?
Yeah,
Yeah.
Because people have the relation between all these 50.
Okay. Great. Yeah, very nice. So you are already using economic theory to explain the data, right? That's what they're doing. So what I'm saying is, suppose we do not consider economic theory at all. We just don't consider economic theory. And we can basically use simple statistical model, right? Line or polynomial or whatever neural network, right? Whatever model you want to choose to model this relationship. You can do that, and you can predict. But that's one way. The second way is to let's come back to economic theory and think about why. Why do we have this relationship? In other words, how are these data actually generated? Okay, how are these data actually generated? Well, in game theory we have models. What is the game theory model? The game theory model is everybody. So suppose there's a person I. This I has a VI. VI is this person's value of how much this object, this painting is worth. And this person is going to write down a bid. So this bid is BI. Okay. So BI is the bid I'm going to pay. Right? I'm going to submit. Now if I win, then this is going to how much I earn, right? So BI is how much I value it. B is what I pay because it's first prize, and then the difference is how much I earn. However, so I want to maximize, right? I want to choose a B to maximize this. However, your B also determines how likely you are going to win. So it's really this times the probability of winning. Winning is your BI is larger than all the other Bs, okay? All the other Bs, right? Everybody else B. Okay? Then you basically choose a BI to maximize this. That's a game theory model, right? And then you basically have to pick a strategy. So the result is, okay? So, so if you choose your game theory model and you solve it, like this very simple thing, you solve it, you have this relationship. The relationship tell you everybody's bid is a function of its value. Okay, so your value determines your bid. Not only your value, but the distribution of the value among people. And that determines your bid. In other words, if you see a person's bid, and if you see everybody's bid, you can use this information to infer everybody's value. There's a way to do that. Okay? Because game theory tells you your value determines your bid. The distribution of value and your value determines the bid. So once I see everybody's bid, I can go back and get everybody's value out from data. Okay, so that's what game theory says. Now, so I can use this VI to essentially get everybody's VI out. That's essentially what I'm doing. And once I have everybody's VI, I know how the value is distributed in the population. I can know this. I can get this from the data. This will be the distribution of V, okay, in the population. Then I can basically predict what happens when I take 50 people. If I take 50 people, that means I basically have 50 draws from this distribution, okay? And the winning bid would be the highest V, and the B corresponding to the highest V. So I can do that, and I can make my prediction, okay? And the result is this, okay? The result is this yellow line is the linear model. This green line is the polynomial. The square model. This red line. Okay, this red line is what? Is the theory, economic theory, which is what I predict. Okay, if my model is correct. Okay, if I just basically the procedure is I use my model to get my V from the bids, and I use the distribution of V to make prediction of what the winning bid is if I include this amount of people. All right? Okay, so you can see, so what's the result? The result is, look, the green line and the red line are very similar. They're very similar. So the quadratic model looks very much just like the theory model, the theoretical model. So why do I even bother with the theory? I can just use statistics, right? I can just use a quadratic model. Why do I even bother? Because the theory model is more complicated to compute. So why do I do that? Well, the answer is, it looks similar here. But once we go out to x equal to 50, they're no longer similar. They look like this. Okay, they look like this. So the red line, according to the linear curve, it will make a prediction like this. Now, the quadratic model is really bad because it predicts something like this. The more people participate, and ends up you have lower winning bid. Okay, the red curve gives you some relationship like this, which is essentially closer to the true data we see. Okay, closer to the true data we see. So these are the true data we see. All right. So the red curve fits the true data better. It gives you a better prediction. So what is the lesson here? What is the lesson here? The lesson here is, first of all, why? Why do we have this relationship? Right? Why do we have this positive correlation? Because economic theory tells us that essentially the reason why the more people participate, the higher the winning bid, is because, first of all, people's value determine their bid. So there's a function that maps from value to bid. And the second, the more people participate, essentially the more you are drawing from this distribution. So the more you draw from distribution, the more likely that your highest draw is a very big number, right? That's essentially it is. So the more people participate, the highest value is more likely to be bigger, okay? Right? So, so if you only, given the same distribution, right? Suppose the distribution is from 0 to, suppose the highest value is 10. So you're drawing from 0 to 10. If you only have two people, then two people participate, maybe they're 1 and a 6, 1 and 4. If you have 3 people, maybe you have 1, 4, 9. But how do you get to 9.99? How do you get this? Well, you need to many draws. Okay. So the more people participate, the higher the highest winning bid is going to be higher. That's the underlying economic reason. But why does it go like this, but doesn't go like this? Well, if you have already made a lot of draws, then it becomes actually harder for you to get harder for you to get even higher draws. Right? I'm sorry. All right, so it becomes harder for you to get higher draws. So that's why the more people participate, it's harder for the winning bid to go up anymore. So that's why it has this decreasing marginal thing, right? That you see. That's the economic theory. Now, in other words, in order to make the correct prediction, we need to have an understanding of what's going on, and we can estimate the economic theory out to help us to make better prediction. Now there are two things. Okay, there are two things to say about this example. The first thing to say about this example is our theory only gives us better prediction. Okay, if there are two if. The first if is, okay, I want to predict something that's far away. Okay, x equal to 50. Right. So remember, this is our data. Our data is x is anywhere between 5 and 25. This is our data. Suppose I want to predict expectation of winning bid. Okay, winning bid. This is what I want to do. Winning bid conditional on the number of people who participate. Suppose I want to predict EY given n equal to 15. Okay, n equal to 15, which is here. Do I need a theoretical model? I can just, I use this green one, right? It's pretty good. Okay, it's pretty good. There's no need for theory. This model is good. Okay, why? Because it's within the range of sample we see, and we can fit it pretty well. It's only when we try to when we try to predict far away, then our theory can give us more reliable results. Why? Because this statistical model doesn't know what's going on. When you fit a statistical model, they don't care what's the underlying mechanism. They just fit it. But they only fit these data, right? They only fit these data. Okay? So they have no ability to forecast what happens when you're far away from this sample. In order to forecast what's far away, you need understanding of the theory. Okay, so that's one thing. Right? So that's the one reason. The second, so that's true everywhere. So think about, for example, you can use your, if you're taking time series, how many have taken time series? Time series? Yeah, you have taken, okay. So we're taking a time, what is time series doing? Time series is essentially a statistical model. There's no causality in time series, okay? So despite the Granger causality, there's no causality. So time series is a statistical model can be used to predict, for example, things like a time series data, like stock market. But you can only predict to a certain degree, right? Very near future, you can do it. If you talk about far away in the future, you cannot do it. If you want to talk about far away in the future, you have to understand what determines the stock price underneath the underlying mechanism. You have to estimate some kind of structural model, the underlying economic thing, not just based on the pattern in the data, because you can only use the pattern for very in sample prediction, not out of this sample a lot. So that's the first thing. The second thing that makes the theory model work. Okay, the theory model works better, has to satisfy two things, right? We talk about first. The second thing is very important. In order for this theory model to be better than the statistical model, your theory has to be good. Okay, it's very simple, right? So everything I've been saying here is based on the game theory model being correct. Not correct. I'm sorry. There's no correct model being good model. Okay, if the game theory model is good, then you do this, and it can give you very good results, better than statistical models. But if your theory is trash, then there's nothing you can do. Okay, your result will be garbage. Okay, if your theory is garbage in, garbage out. So that's really what it is. Okay, all right. So there's a second example. The second example is also shows the power of structural model if the model is correct or if the model is good. Suppose we have this company. Again, I think I give you a very similar model at the introduction. So we have a bunch of data. All this data is different market. Every data point is a different market. Okay. Now in different market, every different market, this company has sales in different market, and the company price is different in each market. Each market, the company sets different prices. Okay. Suppose we're talking about monopoly company. Okay. So there's a monopoly firm. This monopoly firm operates in many different markets. In every market, its price is different. It sets a different price. What else do we see? Well, we see every market's income level. So these are high income markets, middle income markets, low income markets. We also see what the sales, okay, sales divided by population in each market. So you can see there's something like a demand curve here, right? It's not demand. No, you cannot really see demand curve from the data, but there's something has an inverse relationship here. The higher the price, the lower the sales as a percentage of population. Okay, right? So you can see that. All right. So what can we do with this data, right? What can we do from these data? Now, we can, of course, do anything statistical we want. Okay, we can do anything statistical we want. The question is, what can we do if we actually talk about, like, if we use economic theory, what can we get out of this data that we cannot get using any other methods? Okay, if we do not use theory. Well, the answer is this. If we use economic theory, from this data, I can get what? I can get this company's cost curve, and I can get demand curve. Okay, so remember what does economic theory say about pricing? How does a company set its price? How does a company determine its price? What does the company do? In other words, what does economic theory say all this data come from? Like, how do these data come from? Well, suppose you have a monopoly company. How does a monopoly company determine its price? Yeah, very good. Maximize profits. So if there's a demand curve, right? This is your cost. This is your cost curve. This is your demand curve. This is the demand curve. What do? Well, you calculate your marginal revenue. You set, and this is your optimal price, right? This is the optimal price. There's another way to write it. Let me write it another way. Using math. So math basic is you want to determine your price. So your profit is your price times the quantity you sell, but the quantity is a function of your price, right? This is basically your demand curve, okay? And of course, you have a different demand curve in each different market. So I'm going to say this is M, right? This is M, okay? Each different market is a different demand curve because every market has a different income level and different, many other things, okay? So your P times your demand curve, and you minus what? Minus what? Your cost, right? Now, the cost is also a function of how many you produce. The more you produce, your cost is higher, right? Your cost is higher. So the cost is a function of this Q, right? Of this Q, okay? Right? So, but the Q is a function of P, okay? So that's what it looks like. And you want to pick a P to maximize this, right? You want to choose a P to maximize. Okay. So this is our model. Now, does this model describe this data? Now, if you believe, okay, whether this model describes this data depends on what do you think about this company. If this company is run well, so that its pricing is really intelligently made to maximize profits, then you can use this model, right? So if you think that the pricing, the real pricing you see in the data is truly the result of maximizing profit, then you can use this model. In other words, these are the optimal price. So if you believe this company already sets the optimal price, use the model. If you think this company is, again, a garbage company that doesn't know what it's doing, right? So its price is random, then you cannot use this model, right? Because this model says company optimize and make the best decisions regarding its price. So now let's suppose this is a smart company. The price is optimized, okay? So this is optimal price. Then I can use this model. So what does this model tell us? Well, this model says, okay, if I am able to get the demand curve for each market, then I know, if I know that my price is the optimal price, then I can essentially estimate the cost curve. Okay, the cost function I can essentially get it from the data. Okay, right? Why? Because according to our theory, my marginal cost. Okay, the marginal cost of a company is basically its price plus the demand curve, the derivative of the demand curve times Q. Okay, so that's basically just math. In other words, if I can get the demand curve and I know the price, I see the price, then I can get the cost. So using economic theory, I can essentially infer or deduce the cost of this company. Now, do you see the cost of this company from the data? Does the data tell you directly? Of course not. But if you believe its price is the optimal price, then you can actually get its cost curve. Okay, you can actually estimate, get the cost curve out of this data, which is the power of the structural model. Okay, so this is the result. This is the result, right? This is the estimation result. This is basically the, I basically did the estimation. This is my result from the data. So the result is, this red line is the demand curve for one of the market. We have many different markets. Okay, every market has a different demand curve. So this is the demand curve of a median market. This is the cost curve of the company, which is the result of my estimation. And in that market, this is where the company produces. Okay, so this is the supply curve, right? This is where it supplies. So you can see the company doesn't really supply here. It supplies here. Why? Because it's a monopoly, right? So you can do that. Okay, all right. So this is what I estimate. I can know the supply. I can know the cost curve. Now you say, why do I even want to know the cost curve? Well, if you know the cost curve, and you know the demand curve, first thing you can do welfare calculation that you cannot do using if you simply look at the data. But more importantly, you can do things that will allow you that you will never be able to do if you do not use theory. So, for example, suppose these are the data I give you, and I want to ask you, what if the government impose a 20% sales tax on this economy? What happens? What's the pricing? Now, right now, there's no sales tax. Okay, there's no sales tax, and I want to impose this 20% sales tax. What is going to be the new sales and the new price in each market? Can you predict that to me? Can you predict that for me? If you do not use economic theory, there's no way for you to do that, right? So think about how do you do that, right? So I want to know. So I want to say, okay, sales tax 20%. What happens? Okay, how does that affect the market? Now, traditionally, if you do not use economic theory, then the only way you can do this is you let the sales tax be your x. You let price or quantity be your y. If you want to know the effect of x on y, you have to observe many different x, right? And you will see many different y. So what do you do? Well, you go to different country. Many countries have different sales tax, and you see what their price is, or see their, right? But that's a very bad thing to do, because different countries are so different in many other ways, right? Okay, so in other words, traditionally the way to do it, or if you do reduced form, in other words, you have to observe many different sales tax, and you observe many resulting y, and then you can do the causal inference. Right now, if you use economic theory, you don't need to observe all this, okay? You don't need to observe any different sales tax. You can just start from an environment where there's no sales tax, and you can just basically imagine what happens if I suddenly have a new sales tax. How do I do it? Very simple. Look, I already have the cost curve. I already have the demand curve. What does the sales tax do? The sales tax basically just reduce your profit, right? Okay. So for people who have taken Economics 101, the principles of economics, right? So so suppose this is demand, this supply curve, this demand curve. What does the sales tax do? The sales tax, suppose you impose the sales tax, then you basically move toward the difference become the sales tax, and this is going to be the impact, right? You just reduce that, so this become the new price. This is whatever, right? So this is what you learn in economic theory in principle of economics in traditional economic course. And if you ever wonder how do I ever use this kind of model, like is this just theory? No, you can actually estimate all these things. You can, once you estimate the demand curve and supply curve, you can do all the analysis yourself, right? So in theory, okay, I know my cost curve, I know my demand curve, then whatever sales tax does is basically reduce, right? Reduce this profit by what? By 20%. That's what it is. So you basically times what? Times 0.8, right? Reduce, times what? 80%, you basically get it out. And then you can redo the optimization, and you can get all the new things out, okay? So you don't need to observe any other historical sales tax. You can basically calculate what happens if you have all the cost curve and a quantity curve and an estimation. You can do that. Okay, you can do that. That's called a what? That's called a counterfactual simulation. Okay. So what, if you ever heard this term in economics? But in economics we have a term called a counterfactual. I'm not write it. Because I have it here. Okay, counterfactual simulation. What counterfactual simulation means is that I want to predict something that has never happened before. I'm starting with an environment that has no sales tax, and I want to predict what happens when you have a sales tax. The sales tax has never happened in my data. In my data, I have nothing with sales tax, but I want to predict what happens when I have this imagined new thing. That's called a counterfactual simulation. And in order to do counterfactual simulation, you have to do structural estimation, meaning you have to estimate economic theory. Because if you do not estimate economic theory, there's no way to do this. Okay? All right? So counterfactual simulation allows you to predict effects of policies or effects of things that have never happened before. Right? Okay? Like this, right? Like what happens when 丘处机 never passes New Jiaotun, right? So this is a typical counterfactual simulation, which is this something that never happened, but I can predict it. I can predict what happens if he doesn't pass that village. Why? Because if I have a theory about how the world operates, I can estimate that theory, and I can use that theory to predict what happens if he doesn't pass through. That's the essence of structural estimation. Okay, that's the essence of structural estimation. All right. Okay. Okay. So let's come back to this thing to reduce form. Okay. Yeah, let's come back to reduce form. So in summary, what we are doing here is this. In order to estimate the causal effect of x on y, there are actually two different approaches. One is reduced form, the other is structural. Reduced form is this, okay? We all need, in order to estimate causal effect, we all must begin with a model of how the underlying mechanism is. We almost all begin with the underlying mechanism of the model. So suppose I say the underlying mechanism is there's some z that cause x and cause y. Okay, there's some z that cause x and y. Maybe there's something else. Okay, maybe there's a that x causes and the y causes. Maybe there's something like maybe there's something called w that causes y. Okay. So these are the variables that together make up my mechanism. So these are the underlying mechanism that leads to our observed data. We must all begin with a model of the mechanism. If we want to estimate causal effect. Okay? So causal effect estimation is based on our understanding about the mechanism. Without understanding of mechanism, you cannot do anything about causal effect. That's the difference between causal inference and a statistical learning. Statistical learning is purely done on the data. We don't need anything more than data. But causal inference needs data and needs your understanding about what the mechanism is. Okay? About what the mechanism is. It needs a human understanding and a human judgment about what the underlying mechanism is. That's a key difference. We'll talk about more later and later. You will, hopefully you'll more and more understand this point. But okay, so suppose this is your mechanism. Suppose this is your underlying mechanism. What do you do with it? Well, there are two approaches. The first approach is I simply draw a diagram. Okay, I simply draw this diagram. I do not use any math. I just draw a diagram. And once I draw a diagram, I see, okay, let me see. If I want to find out the causal effect of x on y, all I need to do, according to my diagram, all I need to do is conditional on z. Because once I condition, I don't care about a. And in fact, I must not condition on a. If I condition on a, there's no, I introduce correlation. So I do not condition on a. I don't care about this w. I just condition on z. And then I will be able to what? And then e, y given x will actually tell me, conditional on z, okay? Conditional on z is actually represents causation, okay? Represents causal effect. This is called a reduced form. What is structural? Structural is I actually use mathematics, right? I basically use mathematical model to basically describe the whole process. Okay, I basically make this everything I use mathematical model to describe. Okay, which is basically an economic theory. Okay, what is economic theory? Economic theory is basically using math to describe everything that's going on here, the mechanism. And then I estimate everything, okay? I basically estimate this relation. I estimate the entire economic model. And then once I have the entire economic model, I can, of course, use it to predict the causal effect of X on Y, right? Because once I have the entire economic model, I can do anything with it. I can do counterfactual simulation, I can do whatever I want, of course, including predicting the causal effect on X on Y. So that's the difference between reduced form and the structural, okay, And the benefit of structural I already showed you in our two examples. So in summary, this is basically a survey. Okay, so the first 3 lectures, we have spent 3 lectures. I was hoping for 2, but we have spent 3 lectures. It's basically walking you through the different parts of this course. The first part of the course, we talk about statistical learning. How do we learn pattern and then use it to make prediction from data? The second part, we're going to talk about causal inference techniques of how to find the causal effect of X on Y. Okay? And many techniques are reduced form. So for example, suppose I do not have data on Z, what can I do? I can find some other technique, right? So all these techniques about finding causal effects from data using reduced form methods. The third part, if we still have time, then we will actually also cover structural methods, meaning we estimate economic models, economic theory, and use the theory to make predictions that hopefully are more powerful than reduced form methods. Okay, so these are the basic 3 parts of our lecture course. So starting next lecture, we're actually going to our first part, which is study how to find patterns and make predictions using statistical data. Okay, so today let's end here. Okay, let's end here today.